Let's talk about the stability of a fixed point of a dynamical systems. We're going to be looking at it from the perspective of an autonomous dynamical system, one-dimensional dynamical system. And autonomous just means that on the right-hand side, there is no independent variable. In this case, x is a dependent variable. So this is the same thing as dx dt is equal to f of x. And there is no t on the right-hand side. Okay, so I think we can just go ahead and have a definition for this. Definition. So x star is the fixed point, of the dynamical systems or the differential equation x dot is equal to f of x if f of x star is equal to 0. Okay, and then how do we find the stability? We use a theorem. This theorem says that if f prime of x star is less than 0, then x star is stable, is a stable fixed point. If f prime of x star is greater than 0, then x star is unstable, an unstable fixed point. Now, if f prime of x is equal to 0, then the test is inconclusive. So I just want you to note that when we say fixed point, call it fixed point. All right, fixed point. We can also use the word equilibrium point. We can also use the word, what are the words? Stationary point, yeah. Point. Okay, so x star is always a number. So that means the solution x is equal to x star is now going to be an equilibrium solution. Okay. How about we explain this more with an example? So we want to find a fixed point of the logistic equation and test them for stability. Okay, what's the logistic equation again? Okay, let's go with x dot is equal to rx1 minus x. Okay, so this is our f of x. This is our f of x. So all we have to do is set that equal to 0. So if we set in f of x equal to 0, implies that we set rx1 minus x equal to 0. This tells us that x is equal to 0 or x is equal to 1. So these are our two critical points. All right. So our equilibrium positions, our equilibrium solutions are x equals 0 and x is equal to 1. X is equal to 0 and x is equal to 1. Oh, yeah, I should have just said that here. I thought I was using two different variables for some reason, y and x. I don't know. Anyway, so where can we go with this? What else can we do? Or we're also asking the problem to test for the test them for stability. So what do we have? This is, remember that we have the differential equations x dot is equal to f of x, and if f prime of x star is less than 0, then x is stable. If it's greater than 0, x is unstable. So the first thing we have to do is to actually find f prime. So f prime of x is a derivative of Rx1 minus x. So first of all, let's write f of x. F of x is Rx minus Rx squared, so that f prime of x is equal to R minus 2Rx, right? R minus 2Rx. Okay, so let's make our problem a little bit easy. Let's say for R equals 1, let's make R equals 1, right? If R is equal to 1, then f prime of x is equal to 1 minus 2x. Okay, so we now have to look at our two equilibrium positions, solutions, and test them for stability. So now f prime of 0 is just 1 minus 2 times 0, which is 1, and 1 is greater than 0, so that means x is equal to 0, is stable, is a stable equilibrium solution. And then f prime of 1 is equal to 1 minus 2 times 1, which is negative 1, is less than 0. So this tells us that x is equal to 1 is an unstable situation, unstable solution. Okay, so we've answered the two questions there. We have two equilibrium solutions, and one is stable, one is unstable. Okay, let's dig deeper into this. What does this mean? We can answer this with another question. The question, or another problem, the problem is to sketch the phase portraits. Phase portraits of the logistic equation. For R equals 1, with R equals 1, and I would also like us to sketch the trajectories. The trajectories corresponding to a few initial conditions. All right, let's see. The phase portrait, so if we have f of, let's see, let's grab this, copy it, All right. So this is what we want to sketch its face, the face portrait of. Okay. So what the face portrait is to sketch x against x prime. So we want r equals 1 in this case. So if we sketch this, watch what I mean. This is the x-axis, and this is the x prime axis. And we want to sketch, if you look at this, this is a parabola that faces downwards and crosses the x-axis at 1 and 0. So this is at 1. So you have a nice parabola. All right. That. And then what do we have? We have that 1 is stable. Oh, this is unstable. Sorry about that. Sorry, I said that x equals 0 is unstable. It's stable. It's actually unstable. This is unstable. And that is stable. Sorry. Because when it's greater than 0, it's unstable. When it's 0, less than 0 is stable. Okay. So what do we have? This is stable. We're going to fill it in with, we're going to put a dot there, fill dot. This is unstable. We're going to put a circle there. All right. So what does that mean? If it is stable, that means any trajectory that starts here is going to move away from it. And any trajectory that starts over here is going to also move away from it. If you start at 0, you're going to get stuck at 0. And this being stable means that any trajectory that starts away from 1 is going to move towards 1. Okay? So, let's see. This is called a source. It's a source of trajectories, as you can see. Trajectories are moving away from it, and this is called a sink. Trajectories are sinking into it. All right. So, and if you look at this, if you try to find the values, if you find the values, I want you to try this. Find the values of f prime over here. The values of f prime in this region, pick any value, any number between 0 and 1. The value of f prime here is going to be greater than 0. Meanwhile, the value of f prime here is less than 0. So there is an increment happening in this region. Meanwhile, there's an increase happening in this region and a decrease happening in that region. Meanwhile, there is also a decrease happening in this region. Right. Okay. Oh, I meant to do F. Sorry, this is supposed to be F. F is less than 0. And F, pardon me, and I've made 2 mistakes today. I don't like that, but it happens. So this is F. F is greater than 0. Right, yes. And F here, not F prime. F here is less than 0. Okay. So that means that our derivative, which is x dot, right? The derivative of x over here is greater than 0, right? As we can see, the graph is telling us that actually. And f is less than 0, as we can see, the graph is telling us that. And f is less than 0 also here. The graph is telling us that. So we can just use the graph. We don't even need our test, our theorem there. We can just use the graph, plot the graph, and whatever the graph is telling us is what we do. right? If the graph is above the x-axis here, that means f is greater than 0, and there's an increase going on in the value of x. All right. So now let's sketch a few trajectories. So I'm going to draw this here. Make it a little bold. Okay. If that's the case, we have x equals 0. Let's make this our axis, t-axis. This is our t-axis. This is where x is equal to 0. This is our x-axis. All right, this is x equals 0 and x is equal to 1. So we can draw a line over here. All right. This is x is equal to 1. Okay. So now let's see what we're doing again. We have these trajectories. X equals 0 is an unstable equilibrium. X is equal to 0 is a stable equilibrium. Okay. So let's look at this arrow, right? F is greater than 0 over here. So since it's stable, any trajectory will go towards it. Any trajectory coming close to it, starting around close to it, will go towards it. In this case, every trajectory is moving away from me because it's a source. So if you have an initial condition when t is 0, if you start, say, at this point over here, right, it's going to converge towards x is equal to 1. The same thing here is going to converge towards x is equal to 1. And if you start here, it's going to go away from x is equal to 0 and so forth. Okay. All right. So that's that problem. Let's see, what else can I show you guys? Okay, so I want to do a little bit of discussion here. Some remarks. So some discussion I want us to look at. There are three main ways of studying a differential equation, which we're using for dynamical systems here. One is the exact solution. When you look for the exact solution, right? Or what you also call the analytical solution. So this is the method you studied in your regular differential equations. At Manhattan College, this is Math 286. And then we have the numerical method. All right, so this involves like programming, finite difference method, studied in a numerical method course, you know. Example, finite difference method. All right, and then we have the qualitative method. So this is what we're going to be doing in this course, a dynamical systems course. So we're not going to necessarily be solving each differential equations, but we can learn more about the differential equations without solving it, just like we did here, okay? In each method, it helps to know that when a solution exists and when the solution is unique. because there could be more than one solution, you know. So if you have your solution, if you have, let's say you have your differential equations, and you have your initial condition over here, and then you have a solution that goes like this, and then you think, oh, this is the only solution, but then there is another solution that is like this. Which one do you go with? Okay, so uniqueness is very, very important, right? Uniqueness, existence and uniqueness. When does its solution exist? When does a solution exist? Is the solution, is it unique? If it exists, is it unique? Right? Non-unique solutions can be very, very confusing. Okay. So let's do an example here. So we're going to be talking about existence and uniqueness. Uniqueness of a solution. Okay. All right, so let's show that the solution to x dot equals x to the power of 1/3 and x of 0 equals 0 is the initial condition. So show that that initial value problem is not unique. So let's try solving it first. Let's do it in bright blue. So this is the x dt is equal to x to the power of 1/3. This is separable. So this means that let's see, x to the power of negative 1/3 dx is equal to x dt is equal to dt. So it's separable. So if you integrate the first part, you get 3 over 2 x to the power of 2/3 is equal to t plus c. Or you can, this also just means that x of t is equal to 2/3 t plus c to the power of 3/2. I think. Yes. Okay. Yes. All right, so that's our solution. But what is it that we need to look for now? We need to look for C. So if we apply our initial condition, we get that 3 over 2, 0, 2/3, because x of 0 is 0. So when x is 0, t is 0. When t is 0, x is 0. So t is, I'm using this part, to be honest. I'm just using this part. So, okay. So that is 0 plus c. So this just tells us that c is 0. So that actually just means that our solution is 2/3 t to the power of 3/2. So that's our solution. All right, so if you plot this solution, what do you get? If you plot it, you will get something like this. All right, so this is x of t is equal to 2/3 t to the power of 3/2, right? But I want you to observe something. First of all, observe that if you take the derivative of this function, right? If we take the derivative, we have x prime, let's call it x dot, is equal to 3 over 2 times 2 over 3 t to the power of, if we subtract 1 from 3 halves, we get 1/3, right? Yes. So, and that this is our solution. This will just give us what we started with, t to the power of 1/3. Oh, no, that's not what I meant. Okay. So, forget about this. Yeah, we needed that, but I didn't want to spend time doing that this video. So I just want you to verify that this is actually a solution. Verify that it's a solution. Take the derivative and plug it into the differential equation. You get that it's a solution. But I want you to notice that another solution is x equal to 0. X equal to 0 is another solution. So this is another solution. So there's no uniqueness going on here. So when do we know that a differential equation is unique? The solution to a differential equation is unique. Okay? So we do this by following the existence and uniqueness theorem, which is a very fun theorem to prove, but we're not going to prove it in this course. Or maybe I'll give it to you as homework to prove. Existence and uniqueness theorem. So let's consider the initial value problem. Consider the initial value problem. X dot is equal to f of x, and x of 0 is equal to x naught. All right. Now suppose that f of x and f prime of x are continuous. Suppose that they're continuous on R. Then our initial value problem, which I called x, has a solution on some interval. Call that interval negative tau to tau, which is centered at 0. Some interval about t equals 0. And the solution is unique. All right, so the interval is about 0 because our initial condition is assumed to be where t is equal to 0. If it's where, let's say, x of a is equal to x naught, then it will be about a. All right. Okay. So let's look at some examples, or maybe at least one example. So consider the differential equation x dot is equal to 1 plus x squared, and with initial condition x of 0 is x naught. Let's see. If we take our f of x here is 1 plus x squared, and f prime of x is equal to 2x, right? So this means that both f and f prime are continuous continuous on R. They're continuous on R. So let's see. Our theorem says that if they're both continuous on R, okay? They're both continuous on R. So thus, by our theorem, the equation, the ODE, has a unique solution for some open interval centered at 0, at t equals 0. Okay? Now, we have to remind ourselves of certain hidden things there. You have to note that the theorem does not specify the interval. The theorem doesn't specify the interval. And the theorem does not say that the solution exists for all times. All right, it exists for some interval, but not for all times. Okay, so let's see. So for instance, let's go back to our problem here. Consider our problem here. So let's consider this problem. The analytical solution, so the solution that we get when we do it using 286 method, if you do integration, if you separate it and do integration, you get something like this, dt. We just separated it, which means that inverse tan of x is equal to t plus c is a solution. Okay, and if you apply our initial condition, x of 0 is equal to 0, this tells us that c is equal to 0. Just try it. You see that c is equal to 0. So that means our solution is inverse tangent of x is equal to t, or x of t is equal to tangent of x of t is equal to tangent of t. Okay, so that tangent of t is a function that we really understand how it behaves like. So let's see. All right. So there is a vertical asymptote at pi over 2 and negative pi over 2. So this means that this tells us that why did I do that? This tells us that the solution is only guaranteed only in the interval t is between negative pi over 2 to pi over 2, because we want our solution to be continuous. All right, so the highest interval we can get here is from negative pi over 2 to pi over 2. And if we actually start with initial condition being equal to 0, right, then we'll be looking at from 0 to pi over 2. Okay, all right. We're going to stop here. I'm going to stop here, and I will see you in class or see you in the next video. Thank you. Bye.